here. Yeah, please.
Okay.
Professor Wang.
Yeah, Professor Harosh, this is a wonderful talk. It's about history of physics. So you talk in the last, you talk about the two words of wisdom, time and trust. So today, a lot of these research, we have to write proposals, and the proposals are reviewed by a committee.
Yes.
And in your experience, I mean, then the decision is the committee decision to indicate whether this proposals, the proposed research is worthwhile or not.
Yeah.
In your opinion, how often can these committee decisions will produce breakthrough science? Or does a breakthrough science would require something totally, a different kind of look?
This is an important question. Some people have claimed that if Einstein had to write proposals, he would never have been funded. Of course, he did not need funding for what he did, basically, but it depends. Of course, you have sometimes if the research is too new, too novel, that it cannot. It may happen that it is not recognized by the committees which will give the money. I think this is one problem. Another problem, I think, is the fact that you are asked to give milestone and you are asked really to do something that we cannot do. So you are asked when you write a proposal to be in some way dishonest because you have to put yourself into this mold which research cannot really follow. I am talking about basic research here because I understand that if you are in an applied project in which the fundamentals are known, you have to give this milestone. But the problem is that fundamental research is more and more judged and managed in the same way as applied research, and this, I think, is wrong. But of course, we can try to get through this, but I don't think it's the optimal system. When I was much younger, it was a time when the director of the lab had money to give on his own decision money to young researchers and let them work with trust for some time. There are some institutions in the world where it is still the case, but I must say that in France, more and more relies on proposals and on this kind of management. Yes.
Okay, other question?
Yeah, right here. Is it on? Hello. Thanks very much, Professor Harosh. I really don't know how to ask questions. It's really deep, A lot of things escape me. But one thing that is always in my mind, given the quantum physics that you explained, it's very hard to determine a priori whether something is a light is particle or wave.
Yeah.
So it's very contrary to the classical physics that you can predict things, right?
Yeah.
So does it mean that we have lost the ability to predict anything?
No.
Or in an ethical sense, we cannot, we can condone anyone's behavior now because it's not controllable.
The answer is not simple. First of all, what you can predict with a huge precision the probability of events. Quantum physics tells you that a single quantum system evolves, when you observe it, evolves randomly, but you can predict the probability of things happening, the probability of a quantum jump, the probability of particle to be here or there. So it's a probabilistic theory, and Einstein, of course, did not like that. He considered it was a loss of knowledge, and he said that he does not like the idea that God is playing dice. But this is the way physics appears to be, and all the experiments have shown that. But this does not mean that we are working in a fuzzy world and we lost precision. The example I gave with atomic clocks is the contrary of that. The fact that you can have atomic clocks which define time with this precision, and the two clocks will give the same time within 1 second during billions of years, is something that classical physics would have made completely impossible. Classical physics relies on phenomena which do not have this kind of regularity and precision. So there is a kind of paradox in quantum physics. You have uncertainty, relation, and so on, and at the same time you have extreme precision. But it depends what you ask for, of course. Maybe that some people think that at some point you have to reconcile quantum physics with absolute determinism, that we will find the mechanism which leads to this indeterminacy of a measurement, but this is, for the time being, it's a wishful thinking. All the experiments point to this basic randomness of quantum physics. And in fact, even it's even stronger than that. If randomness is necessary, you have a phenomenon called entanglement. If you have two particles which interact with each other and are separated, you will get random result here and random result there, but these random results will be correlated. And it is essential that it is random. If you renounce randomness, then you will be able to communicate faster than light. And this is, of course, contradictory with relativity. So the whole system is coherent in spite and because of this randomness. If you renounce randomness, there is something which doesn't work anymore with the consistency between quantum physics and relativity. Of course, there is still a big question because gravitation has not been included into quantum physics. There is no theory which includes gravitation consistently with the other forces of nature. And some people believe that when we solve this problem, which will require something as deep as what Einstein did a century ago, maybe we will have a clue about this, what happens here. And quantum physics will be a kind of approximation of a larger theory, but nothing tells us that this larger theory will renounce randomness. So.
Thank you very much for a very interesting talk. Well, after so many years, it seems we have understood quite a lot about the properties of light. Do you see any unsolved problems on the understanding of the nature of light? And if there are, what would they be?
I think light as itself is very well understood. You know that the theory of light is what is called quantum electrodynamics. That is the interaction of light with charged particles. And it predicts things with unbelievable precision. For instance, it predicts the magnetic moment of an electron with 10 significant digits, and you measure and you see these 10 significant digits. So there is a huge precision. But of course, light is not alone the only force. And as I said, light is very important because it's almost all the information we get from the universe. And in the universe, there is something that we don't understand. They're missing what is called the dark matter, the fact that there is some matter which is unknown and which does not interact with light. So it's a negative way of looking at things, but you have to understand what dark matter is and why it doesn't interact with light. So these are open questions, but which go beyond electromagnetic theory, of course, and electrodynamics.
Professor, this is an off-topic question. Recently, the British physicist Stephen Hawking was saying that based on his knowledge of the universe, he's saying that there is no God. I would like to hear your opinion on what he said.
I am not, I don't know what to say. I agree with him, but this is my personal view. And I certainly will not engage into a discussion about that. Hawking did, there is another great British physicist, Dawking, who wrote wonderful books in biology about one was called the selfish gene, where he explains the theory of evolution in very, and he spent a whole book to explain that God does not exist. And of course, this book is very controversial because the existence of God is beyond science, and it's something which is in a different realm, and you have to make your personal opinion about that, and I certainly don't want to discuss that. I told you what is my opinion, but I won't explain why.
Okay. As a question? So, yeah, please.
In your talk, you mentioned that we could use lasers to heat matter, but at the same time cool it down. So what is the difference between using the same technology for the exact opposite reason? Okay,
to heat matter is the simplest. It's of course the most intuitive phenomenon. If you just focus a lot of light energy on a spot, you will heat the matter on this spot, and you know that if you focus light from the sun with a lens on you will burn your skin. So this is very simple. What was surprising when it was first discussed is the fact that you can use light to cool. And the process is double. One way to do it is to use the momentum of light, the fact that each photon carries some momentum, and that if you have atoms going in one direction and the light is going in the opposite direction, by absorbing photons, the atoms will be, the velocity of the atom will decrease because it is just absorbing quanta of motion in the opposite direction. Of course, if you want to really to stop, you have to send light on the two sides and make sure that the light which is coming towards you is more effective than the light which is going behind you. And the way to achieve that is to use the Doppler effect. The fact that you know that if you move, you will see the frequency of the light appearing slower if it is coming towards you and faster behind you. So if you put the laser beam slightly off resonance so that this Doppler effect will bring you in resonance with this light beam and out of resonance with the other one, you will be slowed down. And so this is the exchange of momentum between photons and atoms which allows you to cool. And then there are other more subtle mechanisms, but basically it is that. It is the fact that you can control the exchange of momentum between atoms and photons.
Okay, other question? So I have one question. So many people are working on the so-called quantum computer. So
Yes.
from your prediction, first of all, how you think about this, and secondly, from your prediction, when the quantum computer will be faster than today's technology, electronic based, solid physics-based computer.
Okay. I tried to answer with the postcard that I showed in the end. Okay, but to be serious, the idea of the quantum computer is to be able to control qubits, to couple them together, to entangle them, and to use superposition states in a way which will, so to speak, force the computer to compute on different parallel superposition states, and in the end, exploit an interference effect to get the result that you want to get. What I want to say is that, first of all, you have to avoid all kind of decoherence, all kind of loss of quantum coherence, and this is very difficult when the system grows. People have, at least on paper, you can reach a point where you can make corrections. If you code a qubit into a large number of entangled qubits, you can get partial information which allows you to try to protect the qubit from decoherence. Nobody has achieved that yet. It's a fantastically difficult problem. And once you have one qubit, which is, let's say, made of hundreds, one logic qubit made of 100 qubits, you know that you need millions of those to get something which will work. So there are several candidates. One is ions in traps. Another one is superconducting Josephson junctions. It is very, very far from the point where a computation could be achieved. My personal feeling is that this is not, the universal quantum computer is not, will not be obtained with this kind of device. Maybe it will be obtained one day, but when people are trying now, the kind of game people are trying is a little bit like the 1900 game. You know some bricks and you extrapolate what will happen 50 years from now. Nobody knows what will really happen. And I am sure that we'll be surprised by people in 200,000 will certainly think that we are naive to extrapolate this in this way. What is certain is that quantum metrology, not only clocks, but the way we can measure small magnetic or electric fields, for instance, and use that as probes in biology and so on, super resolution microscopy, which is related to this kind of ideas, is already there and is providing tremendous information about the microscopic world and tells a lot about the precision we can reach in measurements. But I have always been skeptical about the quantum computer, but I am very careful. Maybe some ideas maybe it will happen one day, but nobody knows what is the best candidate now to get it. On the other hand, quantum communications, the fact that you can send secret keys using entanglement, for instance, is something which works. The only question is there a market for it? Because classical cryptography is still good, so it's a question of economy, I guess.
So thank you very much. So next time again.
Okay.